On behalf of Barakpur Rashtraguru Surendra College, I am Srimati Purabi Chowdhury presenting a presentation on 8085 Introduction from Department of Computer Science. So let's start. Here, first of all, we have to know the basic idea of computer system. So what is computer system? The basic computer system. A computer system is basically a programmable machine that receives some inputs and store those inputs and manipulates data and information, and with respect to that data and information provides some output in a useful manner. So it is consist of a CPU, a memory and a I/O device or unit. So here is the diagram where you can see that the central processing unit actually the box is there, and the fetching, that is the input device and the output device, is connected to the CPU with another external device is called memory unit. So this is here is the block diagram of basic computer system. So we are going to the next slide. So after knowing the basic computer system, we want to know the basic concept of microprocessor. So microcomputer is basically a programmable machine that performs on a set of specific instructions, and it can execute a list of instructions called program. And the main component of the microcomputer system, that as I already said, that CPU, I/O devices and some memory. And in contrast with microcomputer, microprocessor is a programmable VLSI chip, and the main components of this chip is ALU and some registers and control unit. And with these two things, another term is called microcontroller. So what is microcontroller? Microcontroller is a silicon chip that includes microprocessor, memory and I/O in a single package. So we are going to our next slide. So what is microprocessor? A microprocessor is a programmable, clock-driven, register-based electronic device. So here is the, we can say this is a definition of microprocessor. So what is the meaning of programmable? So programmable means it performs depending on the set of instructions. What is the meaning of clock driven? As we know that any such thing or such devices runs on some clock pulses. So we can say that our microprocessor is also driven by some clock pulses. So this is a clock driven device. And another thing is register based. Okay, why it's register based? So to store any data, we need some register. And electronic device. Electronic device is actually, this device is fabricated on a chip and that runs on some electronic power. That's why it is an electronic device. So here is the introduction of 8085 MPU system. 8085 is developed by Intel. As we, I think here is the first microprocessor that is invented by Intel, that was 4004. So after going the invention, 8085 is developed, and it is a 8-bit microprocessor and can accept 8-bit data simultaneously. So it is a 40-pin chip that runs on NMOS technology. There is many such kind of technologies. Among them, NMOS technology is used here. And this processor runs on plus 5 volt power supply. Also, it runs on frequency 2 to 3 megahertz, has some general purpose and special purpose register that we will discuss in later. It provides 16 address line and 8-bit data lines that has also multiplexed address and data bus. Sorry. We have 74 instructions to program with 8085 MPU system. It provides 5 hardware interrupts like trap, RST 5.5, RST 6.5, RST 7.5 and INTR. It has serial lines like SID, SOD. So, peripherals can be interfaced with 8085 directly using these two signals. Here is the pin diagram of 8085 MPU system. So, as we see that this is a 40 pin IC chip. So, here is from number 1 to number 40, this pin is actually labeled here. So, first of all X1, X2, then RST out, SOD, SID, then like interrupt related pins and so on. So, we will discuss this pin diagram as a whole in later. 8085 pin description. So, some important pins are like AD0 to AD7. AD0 to AD7, that means it's act like address bus and data bus. As we also said that address line and data lines. Okay, so multiplexed address and data lines is defined as AD0 to AD7. Another pins are A8 to A15, that is a higher order address lines, and this is wholly representing the A8 to A15 address lines. Next one is ALE. So, ALE is the abbreviated form and the full form is address latch enable and is an output signal, and it goes high when operation is started by processor. Next pin is S0 and S1. S0, S1 is called status signal, used to indicate type of operations. What type of operation is performing or performed by the microprocessor is actually we can know by using S1 and S0 signal. Next two is RD bar and WR bar. That's called read bar signal or write bar signal. That two signal is actually active low signal. So, read bar signal is active low input signal, whereas write bar signal is active low output signal. So, when we actually use this two signal is used to read data from IO device or memory, or write data from IO device or from memory. Next thing is ready. So, this is an output signal used actually to check the status of the output device. If the signal is low, microprocessor will wait until it is high. Next thing is we are going to explain the interrupt signals. So, first of all is trap. Trap is an edge-triggered highest priority non-maskable interrupts. After trap, restart occurs and execution starts from address like 20024 hex. Next is RST 5.5, 6.5, 7.5. These are actually maskable interrupts and have low priority than trap. INTR and INTA bar. INTR is an interrupt request signal after which microprocessor generates INTA or interrupt acknowledgement signal. IO bar. This is output pin or signal used to indicate whether the microprocessor 8085 working with IO or memory board. Like IO related operation is performing or memory related operation is performing. So, how can we differentiate that? We actually can differentiate using this IO bar signal. If the IO bar signal is 1, we can represent it that this the operation is wholly input output related, and if the signal is goes low, then operation is actually memory related. Next one is HOLD and HLDA. So HOLD is called hold. Hold is an input signal. When microprocessor receives hold signal, it completes current machine cycle and stops executing next instruction. So in response to hold signal, microprocessor actually generates another signal called hold acknowledgement, and this is acknowledgement signal that in response to hold microprocessor generates. Then reset in. This is an input signal. When reset in is low, microprocessor restart and start executing from location 000 hex. That is the first location, initial location. Next, SID pin. SID is called serial input data. Is the pin used when actually we want to communicate with the IO devices like peripheral devices. So when we are actually communicate with microprocessor to IO devices when SID pin is 1. Next is X1 and X2. X1 and X2 is basically these are clock input signals and are connected to external circuit that called LC or RC circuit. So these are divided by 2. So if we are using 6 megahertz to X1 and X2 connected to X1 and X2, then the operating frequency becomes 3 megahertz. And the next one is VCC and VSS. So VCC is the power supply, VCC 5 volt, and VSS is ground in reference. So ground means volt 0, equivalent to 0. This is the whole architecture of 8085 MPU system. Here we can see that the internal architecture or the functional block of 8085 system. So as here we can see that this is a ALU, that is arithmetic logic unit, and the arithmetic logic unit connected with some register is called flag register, and this is also can interact with some register called accumulator or temporary register, and the whole thing can be controlled by some unit is called timing and control unit, and the timing and control unit is connected with the external circuit called X1 and X2. And the right hand side here we can see that the basic registers like temporary registers, the general purpose register and the special purpose register, and the whole thing is called the architecture of 8085 MPU system. So first of all, we are going to explain arithmetic and logic unit or logical group. So most of the operations actually done in a special purpose register is called accumulator. So accumulator is basically a 8-bit register and it is connected to ALU. So 8-bit register, that's why we can say it that 8085 is 8-bit microprocessor system, because the operations that done in accumulator all are based on 8-bit. So it is basically 8-bit general purpose register, some temporary registers, and all the arithmetic and logical operations actually done in accumulator that I have earlier said. A group of 5 flip-flops used to know status of various operations done is called flag register. So flag register along with accumulator is called PSW or program status word. Then we are going to explain arithmetic and logical group. Here the flag register we are going to explain now. So this is the diagram of flag register. So then how to access the memory? So accessing memory actually can be summarized into the basic three steps. The first step is select the chip, then identify the memory register, and enable the appropriate buffer. So, after this, we are translating this to microprocessor domain, and the microprocessor places a 16-bit address on the address bus. So, whenever the 16-bit address is placed on address bus, the part of the address bus will select the chip and the other part will go through the address decoder to select the register. Now, here I/O ember 2 signals is I/O ember and read bar signal combined indicate that memory read operation is in progress. Next going to explain address decoding. So, when the address is actually get the address, the big portion of address bus is usually connected directly to the address inputs of the memory chip. The said portion is decoded internally within the chip. The other part that must be decoded externally to select the chip and can be done either using logic gates or the decoder. Next, we are going to explain the timing and state diagram. A microprocessor actually operates using some clock pulses. So, each clock pulse or clock cycle is called a T-state. So, what is T-state? T-state is basically one time period or frequency of microprocessor is called T-states, and a collection of several T-states is called machine cycles. So, important machine cycles are opcode fetch, memory read, memory write, I/O read and I/O write. So, here is the timing and state diagram that I am explaining here for opcode fetch with diagram. Opcode fetch is actually requires 4 states from 40 states from T1 to T4. So, here is the diagram of opcode fetch. So, here we can see that from T1 to T4, here is the clock pulses. Each clock pulse or each period is differentiated using the straight line, vertical straight line. So, T1 is one clock pulse, T2 is another one, T3 is another one, and so on. So, CLK is defined the clock. Next is define here A8 to A15. Now, what is A8 to A15? That I have earlier explained that A8 to A15 is address bus actually. So, address bus is A8 to A15 that stores the higher byte of program counter, while I/O ember will be low since it is a memory related operation, while I/O ember is a signal. When it's low, it's indicate it is a memory related operation, or when it's high, it's indicating that is I/O related operation. And next thing is A0 to A7. Okay, A0 to A7 is actually used to fetch opcode and store the lower byte of program counter. So, first of all, when the ALE signal goes high at the first cycle, at the first time period, then the multiplexed address cum data bus is called AD0 to AD7 at the first time indicating or acting as low order address bus, and after that whenever the ALE signal goes low, it acting as data bus. Then read bar signal and write bar signal. So, read bar signal goes low at the time of output fetch. Write bar signal will be at high level since no write operation is done. Next to signal is S0, S1, both high for opcode fetch cycle. So, here is the whole diagram. Timing and state diagram for memory read cycle. So, memory read cycle requires 3 T states from T1 to T3. ALE pin goes always high at first T state. Next, address cum data bus, that is AD0, 287 are used to fetch data from memory and store those data the lower byte of address. Next, for higher byte of address, we are using A8 to A15, and that basically store higher byte of the address, while IO bar is equal to 0 since it is memory related operation. Read bar will only be low at the time of data fetching. Write bar will be at high level since no write operation is done. S0 is equal to 0 and S1 is equal to 1. S0 and S1, as we know that these are status signal. So, it is indicating when it's S0 is equal to 1 and S1 is equal to, S0 is equal to 0 and S1 is equal to 1. It's actually indicating for memory read cycle. Next, the memory write cycle. Memory write cycle requires again 3 T states. ALE pin goes always high at first T state. AD0 to AD7 are used to fetch data from CPU and store lower order address byte. A8 to A15 store the higher order address byte, while IO bar will be low since it is memory related operation. RD bar will be high since no read operation is done. And write bar, WR bar, write bar will be at low level only when the data fetching is done. And S0 is equal to 1 and S1 is equal to 0 for memory write cycle. Next thing we are going to explain is interrupts in 8085. So, interrupts is a process where an external device can get the attention of the microprocessor system. Microprocessor system needs to interact from output devices. So, whenever the external devices can interact with microprocessor, this can be treated as interrupt. The process starts from the IO devices that I am explaining. The process is basically asynchronous, and the interrupt here we are classified into two groups, that is maskable interrupt and non-maskable interrupts. Okay, what is maskable interrupts? Maskable interrupts can be delayed or can be rejected, but non-maskable interrupts cannot be delayed or cannot be rejected. So, depending on the vector location, the interrupts can also be classified into another two groups is called vectored and non-vectored. So, what is vectored? Vectored is actually the address of the service routine is hardware, and non-vectored, the address of the service routine needs to be supplied externally by the device. An interrupt is considered to be an emergency signal that may be serviced. The microprocessor needs to respond to it as soon as possible. Interrupts in 8085. The 8085 has 5 interrupts inputs. The INTR input. INTR input is the only non-vectored input. INTR is actually a maskable using the EI or DI instruction pair. RST 5.5, RST 6.5, RST 7.5, that's called a restart interrupts, are all automatically vectored. RST 5.5, 6.5 and 7.5 are all maskable type of interrupts, where another interrupts is called trap, is the only non-maskable interrupts in the 8085 system. So, trap is also automatically vectored interrupt and it is a non-maskable interrupt. So, here is some list of interrupts. So, non-vectored interrupts in 8085 microprocessor system, there is restart instructions like RST0 to RST7. Each of these would send the execution to the predetermined hardwired memory location. So, restart instruction equivalent to some locations. So, RST0 call some 000 hex location, RST1 call 0008 hex location, RST2 call 0010 hex location, and so on. So, last thing is RST7 that call 0038 hex location. Here is the priority. So, among those interrupts, the priority should be calculated. So, here is the interrupt name and maskable and vectored classification is there. So, trap RST 7.5, RST 6.5, RST 5.5 and INTR. So, priority wise, trap is the highest priority, and after that after trap RST 7.5, then RST 6.5 and RST 5.5, then INTR. So, INTR is the lowest priority signal, and trap is actually maskable. Here the column said that no, the vectored yes, RST 7.5 this is maskable. So, column said this is yes, and the vectored also said yes, and RST 6.5 that obviously maskable and vectored, RST 5.5 and this is also maskable and vectored, but INTR is maskable is yes, but vectored no. So, INTR is non-vectored interrupt. So, thank you for your patience, and that's all for this time.